Hi, hello everyone. Welcome to today's reading group, where I will share some of the papers that I recently read about the spread of the opinions on social networks. Oh, okay. So, a quick outline of today's presentation will include in two parts. First, I will quickly go through the background, and second, I will go into those details of those models and mention like what kind of inspirations we can get from those papers. So my motivation comes from part of my previous work, where I already studied how to infer opinion from relations or from the text content of the posts, or like to be specific from the tweets. And if I want to do something more, it is quite natural that I need to think about the spread of the existing opinions and how opinions are getting influenced by others. It's like how people exchange ideas and change their position. And also, most importantly, when thinking about the social medias these days, I find that almost nobody is satisfied with the online environment, but we don't know how to treat this kind of problem yet. Like we don't know how to spread some opinions that we find will be beneficial to the society, and we don't know how to alleviate some of the argument, some of the, like, for example, pro-science and anti-science debates that's been going on forever. And so from this perspective, it is quite natural to think about like how to model the opinion dynamics. And recently there were a paper on predicting opinion dynamics via sociology informed neural networks from KDD22. And also, like, there are some other approaches that I would say that they are trying to analyze something from the observable data from the real world online community. This include the effect of word in a message propagation. This is a work from ACL year 14. And some other papers that I'm going to mention here, I put a star mark on it because they are kind of like I am only mentioning part of those papers, like not the whole, not the entire paper. Yeah, and so let's get started from the first part, where we start from the opinion dynamics models. The first time I see those models were from this paper, the sociological informed neural networks, or we say SINN. And for this work, they already released their code, and you can actually run it. And the data is not available, unfortunately. They provided their crawler script that you can use to crawl data from Twitter and also from, I think it was Quora, another platform that they use. The method they propose is that they use neural networks to model opinion dynamic models, or like they are trying to prove by experiments that neural networks are capable of acting as the opinion dynamic models. And they are not really considered the network structure, the social network structure, such as the follower-followee relations. It's missing from their, completely missing from their data. And they are claiming that they use the ODE framework to learn the parameter of the social dynamical system, but they are not using the VAE for, variational autoencoder for learning. That is, like, they are not, unlike the other, most of the other neural ODE works that we can see, where a trajectory is predicted and compared to the ground truth observations, it's not the case. They are kind of modeling from step to step. And in particular, the model that they are using is relatively straightforward and quite simple. It's like first they define that from step t to step t+1, I consider a single user XU, and given a opinion dynamics model, which we currently, let's call it F, and with some parameters, let's call it theta, and we predict the value at time step t+1 as this. And where X are all the nodes opinion, can be all the nodes opinion in theory. And F, this F, will include some learnable parameters. And also, because they are saying that they're using a neural network to handle the work, so what they do is that, well, no, and they also use an MLP net G5 to model the dynamical system. And I'm putting a link to the code here if you are curious in the detail. But those this MLP is the structure is mostly quite simple. And something to note is that somewhere in their code they mentioned the term attention, but this term is mentioned casually. It does not mean that they include any attention mechanism. What they actually do is just computing a learnable weight or something like this. And by having this kind of structure, like using a MLP to model the dynamical system, while together with some underlying assumption that there should be a opinion dynamics model F that's could be used to model the changes over time. They are computing a loss like this with a lot of regularizations. That's like especially the middle term, which is LODE, or we say that this is the difference between the SINN model's gradient, that is the gradient of G over T, that is fetched via this function torch.autograd.grad, and the ODE gradient that they are trying to learn at the same time. And some other terms are evaluating how accurate the prediction is, and how well the not how it's like and the last term is just a regularization term on the parameters of the of F, which is like the parameters of the ODE functions. And those models that they mentioned, those opinion dynamics models that they mentioned in this paper is probably the most interesting part to us. And a brief introduction on this part is that the opinion dynamics studies how opinion emerge and evolve through exchanging opinion with each other in the system. And in general, I mean, there could be some exceptions, but in general, this kind of problem settings goes like this. Like we have a set of users and each person, let's call it a lowercase u, that person holds opinion XUT, which ranges from -1 to 1 on a specific subject at time t. And the user's opinion will affect each other. And this model uses some math formula to model how opinions are updating from any time step t to the next time step t plus 1. And the most the most obvious differences between any two models are that they have different update rules, which means that there will be different versions of f. I mean, that this f, as we mentioned in the previous page, which refers to the underlying dynamic rule. Yeah. And almost every time when you see someone talking about opinion dynamic model, it starts from de Groot, which is probably the simplest one and the most basic one. And in this model, it says that every user's opinion gets updated through its by summing up its own opinion and everyone else. And everyone else's opinions are kind of like but the importance of anyone else's opinions can be different, controlled by a parameter AUV that denotes the strength of the interaction between U and V. And you can interpret it as like the closer that your relation with somebody is, the more the easier you get influenced by that person's opinion. It's quite intuitive from this perspective. And it is said that this model models the assimilation pretty well, which like assimilation is the idea that people have the tendency of moving opinions towards each other. It's like when you see someone else have some opinion, you tend to agree to it. And in the SINN paper, this model is factorized like this. It's like using some matrices to decompose the parameters of in this field AUV. And because the previous model only models the assimilation relations pretty well, and we can also think about like people tend to stick in our own opinions. It's like so there comes the next model, that's Fredkin-Johnson model, that's or FJ model. It allows for some sort of stubbornness. Yeah. Mm-hmm. So F and Q here, so these are the learnable parameters. They are learnable. Okay. Yeah. And they are like a one row column in a matrix. Yeah, they're just they are simply trying to decomposite such kind of an n times n matrix so that we don't have to learn all the n times n parameters. That's what they are doing.
Okay.
Yeah. No, by the way, all the parameters that's get mentioned here are learnable in their model. Yeah. And here, okay, let's see. So FJ model, it allows for some stubbornness. And the main difference is that, so first you can see that XU, and instead of considering XU's opinion at time t, this version actually considers XU's opinion at time 0. Where time 0 refers to the beginning of the time, which means that people have this tendency of staying in our original position. And SU is a parameter that's used to denote a feature that's called the susceptibility to persuasion, which means that so this idea means that the tendency to defer to others' opinion, and when they sorry, this line is incomplete. I mean, the larger SU is, the more open-minded a person is. Like, as you can see, if SU tends is like getting close to 1, then it means that this person is not sticking to its original opinion. And it's also getting transformed into a derivation form, and gets the ODE version in SINN.
So why in the end we have the last item?
I think this is because when you compute the derivation, we need to compute XU t plus 1 minus XUT, and like somewhat compute this deltas over that delta t. So
Sorry, I think you're talking about the discretized version, but why in the continuous version we have that last item? I think in some model, like epidemic model, they have the last item, which is related to self-recovery or something like that. In this opinion model, what does that mean?
Well, my previous understanding is really that, yeah, my previous understanding was that we needed to model the changes over time from t to t plus 1, but yeah.
But here's the continuous version. Probably that's kind of self-correction, right? So similar to the epidemic model. When more people get sick, then it means that more people will get recovered. And here is like, I fear when you got more extreme, then somehow you have this self-correction. So that move you to the other direction.
Yeah, probably we can interpret it this way. Yeah.
Did the author mention the reason in the paper?
No, not at all. And yeah, they're not saying why there is a term this, but they are saying that this is the equivalent version of the ODE. And I double confirmed that in their code, and it is indeed what is written down in their code.
Well, when I say equivalent, then I have to prove, even from like discretized version,
Yeah.
like then use some limit, right? We can prove to the continuous version, then that means it's equivalent. Right? Do they show something like that, or just mention it's equivalent?
They just mentioned it, no, not showing anything.
Okay.
Yeah, because actually they are showing a whole list of different versions of dynamic, or opinion dynamics models. So I think it's just like a part of their, yeah, like a one. You can regard this as like one baseline of their model or something like that, or one version of their model.
Mm-hmm.
Yeah. I think the kind of model that they regard as the main model, or like the main focus, the default version of their model, should be the bounded confidence model and the stochastic bounded confidence model, these two. And for the bounded confidence model, it grows a little bit more complicated, but just a little bit. So basically, the bounded confidence model, it's a family of model. Like we cannot say that all bounded confidence model looks like this, but the most popular variant is called the Haxelman-Kress, or like HK model. This model has the notation like this, where we can regard this as like a user U at time t changes opinion according to a group of user in the set NUT, and and then gets its opinion in time t+1. And where the NUT is the set of the users whose opinions fall within the bounded confidence interval of user U at time t. So the bounded confidence interval is the reason why we call this a bounded confidence model. And NUT is like defined this way, like when their opinions are close enough. And oh, by the way, this sigma is again learnable, and it's like within a bounded confidence interval of user U at time t. They have the potential of influence each other, otherwise they're not. And and the ODE version in SINN, it actually uses a sigma function to kind of like if it's smaller than 0, then that's 0. And so like what else? Okay, so for this model, I think the intuitive understanding is that like you only wish to listen to those opinions that are somewhat like somewhat similar to your own, so that you can understand what they are saying, so that you don't suffer a lot from trying to understand their opinions. Yeah. And the next model along this line is called the stochastic bounded confidence model, which is like, actually this is also a family of model, but the version that's getting used in this paper is listed here in this in this equation, where people use a score function. Let's call it a P, or like PZUVT. This is used to model the probability that U and V, these two users, interact at time t. And the reason why we call this a stochastic bounded confidence model is like it allows for, so the previous model like this, it's saying that everyone is interacting all at once, like everybody is interacting together. And this SBCM model allows for like probably you can select to interact with only a subset of users quite easily. And the rho here is used to control the, is used to control the tendency. Like if I think like I think it was like when rho is smaller than 0, it's like the more similar the more similar users are interacting with each other, and or the opposite times. I'm kind of getting confused on this part on my own, but let's see, rho to the power of minus rho.
So what's the range of this rho? Is it like a positive?
A real number.
Could it be negative?
Yeah, and I don't think it will be equivalent to 0. It's like, I think okay, so rho is in the range of negative value or positive value. One of it corresponds to the case that you want the most similar users to be most likely to interact with each other, and the other case represents that you want the most different kind of person to interact with each other in your system. And I think there were, yeah.
So that means when rho is big, then the similar users should be.
Yeah, probably, yeah. I think one, yeah. It's like divided by 0. It's like kind of a parameter that controls the way that people gets interacted with each other. Okay, and when this model is transformed into the ODE version in SINN, it starts from using this like ZUV time t to apply to the weight of like the influence of any user V on user U, and this ZUVT is computed via a softmax, like computed from this previous P that were already given, and this. And also plus a G, which is a random noise, and the random noise like uniformly sampled from some distribution, and tau is a temperature parameter, which like when it approximates 0, then ZUT approximates 1 hot. So it's like one user interact with only one user at a time.
So for this part, I think in the first place, we want to utilize this XU and XV to calculate the potential inference score between U and V. So that's why we do the calculation for TZ UV equals 1. But then later, why this V UV tilde T is computed using a different formula?
UV.
So in the first line of the formula, we try to calculate the score for each pair of nodes, right, U and V, at any time stamp T.
Oh, sorry.
So
Like
we-
this P is not computed by this time, but okay, let's see.
I expect that we're going to directly utilize that probability in the propagation formula.
Okay, I see. I think so to my understanding, it's like the reason why this is the case is because they want this whole this whole opinion dynamics model to be trainable, learnable, and it's able to be trained together with a MLP network that they propose as their so-called SINN model. And let's see. So
I say in the first line is like from the origin model, and then
yeah,
afterwards they try to propose like a deep learning based version.
yes, a deep learning based version.
Okay.
And this is okay, so let's go a few pages back here. It's because like in this equation, not only F is getting trained, but also, not F, sorry. Not only G is getting trained, but also F is getting trained at the same time. It's like these two models are somewhat getting trained. This two model that I refer to as like one of this is the MLP model that they are trying to use to mimic the dynamic changes within the system. And the other model is the ODE function that's used to model the opinion dynamic model in theory. They want this to agree with each other, and they are trained this way. So G has to be something that's learnable, and has to be, yeah. And so they use this kind of function to make it learnable.
I see. So formalization wise, I think probably in the very beginning, if they write down this X hat T plus 1, so in their earlier formula, they just write down it as like G function, right? But then later when they say ODE version, actually they are always talking about their gradient. So I think probably it's better for them to, like in the very beginning, they also try to say, oh, I want to utilize a neural network to approximate the ODE function, the gradient. So that will be easier for us to understand, right?
Yeah.
Yeah, because later they're always talking about the gradient instead of the X hat T plus 1.
Yes, they're always talking about the gradient. Yeah. And the gradient itself is what they call an ODE function. Yeah. And yeah, so those are like until this page, we have covered those models that they have mentioned in their paper. And maybe this is kind of like counterintuitive to us that they are not, like none of those models are using a social network graph structure. It's like we are not even consider the interactions like follow or being followed in a network. But something that I also want to mention is that there are already some existing work along this line that's already get the adjacency matrices of a social network into consideration. And for example, this work, where we say that IU is the set of account to which account U is receptive to, and W is a predefined hyperparameter, and the A is the adjacency matrix of the network, and the F is a function that could be defined like when some condition is satisfied, then it's 1, otherwise it's 0. It's simply like something that's controlling how XV should affect XU's opinion. And W, yeah, W is a parameter that we already set. And this formula is from this paper, a model for influence of media on the ideology of content and in online social networks. And this model, this paper talks about the influence of media in particular. It's not like generally exchanging idea, it's media. And so that's why they have M and N, where M denotes the set of media and N denotes the set of ordinary accounts or like normal accounts. And so a lot of their consideration is about how to deal with the social the medias like CNN, BBC, such kind of special accounts. So yeah, probably it's important to keep this in mind because maybe not directly applicable to all kind of situations. And but this expression, as we can see, it's probably getting more similar to what we usually have as a GNN model. And yeah, and so there are trends of considering next network structures already. And some of my conclusions on this line of work is that like some efforts were made to bridge the gap between opinion dynamics model and powerful computation tools like the neural networks that we have here. And some recent works are considering graph structure in modeling the social influence already. And so where the gap comes from, I think it's because the opinion dynamics models are generally having very strong assumptions in the first place. And so it means that they might be having a good performance on a carefully designed, like simulated data or like a carefully selected subset of a real world data set. But if we want to apply it to a massive amount of nodes on a real world social network, it could be a problem in practice. And in fact, previously I have tried to apply this SINN model on the data that I collected from Twitter, and I think the results were generally bad. And if you look at their paper to see their results on the real world data set, and the results are not that high either. Okay. And so another line of this work starts from the observed real world data from the online communities to try to find something from there. And one of the very, I think it's somewhat popular. This work is called The Effect of Wording on Message Propagation, and topic and author controlled natural experiments on Twitter. And which I would maybe later on refer to as effect of wording. And this work investigate whether a different choice of words affect message propagation and controlling the speaker and the topic. And this is like this propagation is measured by the number of retweets, and this kind of work usually have quite similar ways of measuring the propagation or like engagement. Like in a work, I think actually the latter paper that I list here cited the previous work, the effect of wording. It's like it's the second one I list here says like it's a picture worth 1,000 words, an empirical study of image content and social media engagement. And this work investigates the influence of image content on social media engagement in an empirical way. And the engagement is measured by the number of retweet and like, and the like maybe not retweet because they include Instagrams as well. So it's like a similar things, like how they are repost and how they were liked. And I will say that the work, the effect of wording, this paper really did a lot of work. They really they really put a lot of efforts into every step, starting from data collection all the way to analyze. Like there's not an easy step in this work, and probably that's the reason why their work becomes somewhat influential, somewhat popular. Yeah. And it starts from the whole story starts from an observation. That's actually, this observation is proposed by someone else in an earlier paper that gets posted in year 2008. It's like it is unexpectedly common for the same user to post different tweets regarding the same URL on Twitter. So this is like okay, so I don't know how many people are using Twitter instead of other social network platforms like Weibo or something else. In fact, Twitter doesn't support long text that well, at least before, like, I mean, at least right now. I think Elon Musk, after he takes charge of Twitter, he said something like he would start like some new functionalities, like getting a better support of long text, and don't have to, like, then you don't have to paste images and URLs on there. But in fact, like as it was the case before, so when you are trying to say something that's like cannot be described in a short text, you need to either paste an URL or attach an image or do something like that to work around. And so sometimes the user set something and post an URL, but for some reason they say something else and paste the same URL again. And so those users, starting from this observation, they collected some pairs that they call a TAC pair, TAC, which is topic and author controlled pairs, which means that those pairs contain the same URL, and are coming from the same account. And they refer to the previous tweet as T1, the later tweet as T2, and the corresponding number of retweets being N1 and N2. And some of the examples from their data sets that we can see here, includes like some different descriptions, like different introduction, the different introduction, like or like promote words or something to the same URL. And sometimes they're pretty similar and sometimes could be different. And something good about this is like they do provide their data on their page. So if you are interested in their data set, you can directly get it. And for their model, their model is not very complicated. So basically they spend a lot of effort onto creating or like crafting these features. They have okay, so I say 3 versions of features because they are usually they're usually comparing their customized feature and the unigram feature and the bigram features. And so this is why there are 3 versions that I say. And so the one that they spent the most efforts in is, of course, the customized one. The customized feature is like is the combination of all the 39 features that they come up with from, like, actually they don't come up with those features at random. For most of those features, they have something to cite. Those features are coming from some previous work, previous analysis on what kind of factors can affect like how appealing a tweet is, or something like this. And those features include that whether or not it asks people to share explicitly, or like, is it using the first person singular, or like a sentiment wise, is it positive, negative, or neutral? And is this piece of tweet being informative, and something like this. And those features are independently, relatively independently designed according to a lot of previous works. And if you are interested in it, I really recommend you look into their original paper, because like, I think there's no way to go through all the details of like how they crafted those features. And any feature can be actually used independently. I mean, like, for example, just to apply this single feature into their model to see how well the outcome is. And what else? Okay. And also they have because as we can see, they have they have a lot of tag pairs, the topic and author controlled pairs. So they definitely would have a classifier to tell to tell which one is more popular than another one. Or like, to be more specific, it is trying to tell which version of the tweet gets more retweets. And they are using just as simple as the L2 regularize the logistic regression algorithm. And also they compared with SVM. And what they are claiming is that the performance gets somewhat close, but the L2 regularized logistic regression performs slightly better. And also they propose a strong baseline, which is also using an L2 regularized logistic regression, but not using the tag pairs for training. It's like it's not having this paired up structure. And but like in order to make this a strong baseline, on top of the existing features, they also add some new features, like they add the day and hour into this into the feature, and also the follower count of that particular account. Yeah, and it's like they are adding a lot of things, but they are removing the tag. So this baseline is like for them, they designed this baseline and use it to emphasize how useful those tag pairs can be. And they did some justification, which is like, yeah, maybe one of the advantage of their papers, like they try to think about a lot of details in a very systematic way. And so first, the question comes about that, do the wording effects really exist? It's like, does the wording really affect how popular a tweet can be? And so in order to examine this, they asked 106 humans to predict, they throw their tag pairs onto those humans on the Amazon Mechanical Turk experiments, this platform, which uses some crowdsourcing. And it's like they ask questions, ask the humans to predict which version should get more widely spread. And the accuracy, the average accuracy of human behavior is as high as, not as high as, I mean, as low as, or like, but it's better than random guess. It's like about 61%. So the conclusion on this step is that it is somewhat possible to predict greater message spread simply from wording. And also they are thinking of like probably time can matter a lot. Like for example, although I post 2 tweets with the same URL, but one of the tweets I posted a year ago, and back then no one noticed that, for example, that phenomenon or like that kind of story. And when after a year, like now something happened and I posted again, and people have different reaction, and it could happen that way. So like 1 year is maybe too extreme a case that I say here. Normally the time difference is counted in days, and so they want to evaluate like what's the like what kind of time range should they allow for a valid, reasonable pair that's is comparable enough. And so they used a scoring function, or like a computer value like this, to compute some sort of score, where here we see the E. The E is the average value of N2 over the pairs where T1 are retweeted N1 times, which is to say, how to say? So it's like, okay, so N1 and N2 are the number of retweets that's T1 and T2 get. Oh, sorry, maybe I shouldn't use like a T1 minus T2 here, because T1 and T2 should refer to the tweet content instead of time. Sorry for this confusion. I will correct it later. Yeah, but anyway, it's this value, and it's like the lower the D value is, like the more reliable, like this, or like the more stable, or how to say, or like the more reasonable choice that's being made on T1 and T2 selection. So this value is used to like they are trying different time lags, and finally they decide to, I think it was like within 12 hours of time difference. Yeah, this is, it means that they did not make those design decisions at random. They do something to justify it. And later on, they focus on evaluating some of these aspects, like they evaluate how effective a feature could be, like measure whether or not having this feature will result in attracting more retweets. And they also evaluate author prefer, which means that this feature is more oftenly seen in the author, how to say, so it's like for the authors, it's like this feature is more oftenly seen in T2 than T1, because it's like the way that we understand it is like because there must be a reason why I post another tweet with the same URL after a while. Normally it's because like I believe doing it this way is better. Like for example, I'm not satisfied with my previous wording, or I'm not satisfied with my previous outcome. Like I think this tweet deserves at least 10 likes, like and 10 retweets, but why does it only gains 2? I think there must be something wrong, like and let me do it again, something like this. So the author preference is measured by like how likely that feature appears more in T2 than in T1. And also they measure the feature coefficients, which is like how well the model perform using that particular feature set. It's like they are having the same model, but feed in different features to try to predict try to predict which tweet gets more widespread. And so the underlying assumption is that the better that feature is, the more useful that feature would be to in terms of making a tweet popular. And oh, by the way, the conclusion, I think the conclusion was that the customized feature, which is like using all that many features together, gets a extremely good outcome. And okay, actually not that extremely good, because it's like the performance is much higher, but in general, the performance is still, let's say that the prediction performance is about this level. It's like using that baseline is like 55.3 like this, and human prediction is about 61% accurate. And by using TAC and regression model that is pretty simple structure. It achieves the performance as high as like 65.6, which is at least much higher than human, and also higher than the baseline. And also there include some findings like some of the user preferred features are not that effective, which is like sometimes when you want to promote your tweet, you try to add a lot of mentions and a lot of things like this, but those features are generally like according to their analyze, these features are preferred by a lot of authors, but not really help you get in more retweet. And so it's and just a quick recap that this piece of work is like the whole story starts from the observation that there are a lot of tweets from the same user with the same URL, but have different wording. And based on this observation, they created data sets that we call the tag pairs. And there can be other ways of pairing the data up. Like for example, in the following up work called like is a picture worth 1,000 words, an empirical study of image content and social media engagement. In this work, and they have a similar data source which collected from similar social media platforms. And they have a similar ground truth, which is like retweets, likes, such kind of things. And the scope of the data they narrow down in this picture engagement work. They narrow down the scope to mostly the commercial posts, like some sales of some cars and airlines and etc. Because like this is somewhat like they have to do this because they are focusing on the pictures, and not everyone is that enthusiasm in like posting pictures, but like when people are trying to sell something, they usually do. And but the interesting part about this is like they have a different way of finding pairs. Like as they claimed in their paper, they used the propensity score matching approach to create some pseudo treatment group and a pseudo controlled group. Like they match it one-on-one on the basis of posts and account characteristics. It's like they are like among those that are those post and account characteristics, and they kind of like find those posts that have those similar features, and they use the propensity score to actually they did not describe it such much, but according to my understanding, please correct me if you think that I made some mistake here. It's like they use the propensity score matching approach to estimate how likely a certain tweet is like getting a certain treatment. I think this is by definition how a propensity score is used to. And also like later on, they use some again, they use some very simple models like logistic regression and multinomial naive Bayes, linear support vector machine, and random forest. And by the way, they claim that linear support vector machine has the best result among those models that they tried. And something that's like, so far, this is something that I understand about the propensity score. It's like we have so the story starts from treatment effect. This definition, it's define, like, let's say that there's a tau I, which is the difference between yi1 and yi0, where yi refers to the outcome of whether or not a treatment Y is applied to this sample I. And when there is a treatment group and the controlled group, and we have an average treatment effect that can be estimated this way, like expectation of the difference of yi and y1 and y0 over a lot of samples. And the propensity score is something that is used to estimate the likelihood that a treatment is applied to every sample, where D here refers to whether or not the treatment is applied. And this piece, those informations are like concluded from like Wikipedia and a lot of other pages that I found online, like about the propensity score. And this work used the propensity score to create a pseudo treatment group and a controlled group. And some of those limitations in this line of work and some of the conclusions I have is like, first, we find that labeling is hard even to human beings. Like normally, like in a lot of work that many of us have worked on before, by having a human labeling, we usually can achieve a very high accuracy, like easily being higher than 80%. But in this, in the previous work, the effect of wording, we find that human achieve an average accuracy of only slightly over 61%, which is definitely means that this kind of work itself is somewhat difficult. And also, everyone is figuring out some ways of to get away from the difficulty of finding counterfactual pairs. Like some are looking for the pairs that contain the same URL, and some are and some are trying to create some pseudo treatment group. And also, like as part of the nature of a social media, because like we human society is not living entirely in the online world, there must be some offline information that's being very influential, being very useful. But by observing the online world, we totally lose track of this part. And of course, another big problem is like most problems that we study by observing the online data, they are not well defined, or like at least not predefined. It can be hard to convince others, convince your audience into agree with you that something that you are studying is like from the topic to the methodology is worth studying in the first place. It's could be hard to convince them into your storyline. And also like when I see this paper that's called an integrating explanation and prediction in computational social science, but I wouldn't recommend you read that paper because as you can see where it's get published, it's on it's on Nature, I think. So it means that it's not that computer science flavor. It's more or less it's just advocating that we should do this. Like the whole paper is talking about we should integrate explanation and prediction into computational social science. But I find that some observations or some insights it has on social science and computer science are pretty reasonable and worth mentioning. It's for the social science, their pros are that they always easily come up with some interpretable manner of describing things, and they are explainable. Their models do have a lot of reasons to back them up, and they always use some causal mechanisms. It's quite often seen in their work that they say that this factor caused something and that factor caused something else. But they sometimes fail to predict the outcome of interest. They fail to offer some real world solutions. And because some of their works are based on some very limited observation, it's not easily scaling up to a very large scale. So it sometimes fail to replicate results when we change the settings. And computer science is something that we are more familiar with. It's the good thing is quite obvious. It's good at designing accurate predictive models. And of course, as a result, it's computer science almost always could generate some predicted outcome of interest. And it's easier to provide some practical solutions to the real world problems. But the cons are there can be traditionally, we neglect some of the causal mechanism, studying causality in computer science can be a very large challenge. And we don't usually care whether or not our models are interpretable. Sometimes a black box, or sometimes we do have some reason for that design, but we don't care that much about whether or not every detail is explainable. And in that case, our model being learned is easily biased. It could be biased for many different reasons. For example, we just by default agree to all the observations that we find in the real world, so that the data itself is biased, and could be that the way we design our model have some pre-assumption in mind, and we are also biased for some reason. But anyway, the outcome is good according to some measurement of the score. And this is so far the challenge. And it's if we want to study or analyze the social networks better, maybe we'd have to go into those details. There's a paper gets shared here. And yeah.
So I just shared a paper. It's a survey paper about how we can combine deep learning and the traditional causal inference to solve some real world problems. So it's a survey paper, and Song and Bernard Couch Bernard actually is from social science, so that's why but he's very interested in computer science and deep learning, and
I see.
he actually lead this survey. I think it's a very interesting reading because Bernard is kind of familiar with both deep learning or machine learning and the social science. So I think this survey is quite accessible. So if you're interested in this direction, probably you can read this.
I see. Thank you so much. And I think this is so much I have for where is that? This is so much I have for today's reading group. I'm just like sharing some of those interesting and also like yet challenging part of like trying to move one step forward into analyzing the social networks better.
Yeah, that's very good. Okay, thank you, Patricia.
Thank you. I'm going to stop sharing now.